Hello, my name is Charlie, and I'm one of the CPSC 213 TAs for the 2021 Winter Term 2, and I've been TAing this course for 3 terms now, and we would like to make a video to help you and guide you through how the 213 simulator works. So this video is going to be split into kind of 2 parts, where first I'm going to be going over the interface and the functionalities of the simulator, and then I'm going to walk through a sample program that I have and explaining what each of the instructions do relative in the simulator. So to begin, what you'll probably want to do first is to download the Simple Machine 213 jar off the website. This is just the assignment 1.2, and you definitely want to get this version of the Simple Machine and not test your code on your own student version, because that could be bugged sometimes, and sometimes people have questions of why their code isn't running right, and it just turns out they were running it on the non-reference version. So once you download its jar file and make sure you've installed Java, what you can do is here I have that Simple Machine jar in its folder, and in order to run it, we can open a terminal. I'll just open Windows PowerShell. If you're using Linux, you can use the Linux terminal, and I will just do java-jar. It's kind of dark, but you can't see it, and I will run the Simple Machine. And it opens up something like this. So I'm going to make this full screen and increase the size so you guys can see the text a bit better. So this is what our Simple Machine simulator looks like. You can see that up here at the top it says solution, so you know that you're running the right version. And just to introduce you guys into our interface, for SM213, our machine has 8 total registers that are shown up here, and they're labeled R0 through R7. And here we are seeing the values that are stored in the register. When you first open the machine, it's all going to be set as zeros. And over here we have interpreting the values, whatever is in the registers, as either an integer or as a reference. And you'll see how this reference column works a bit later when we load an instruction. Down here we have kind of the how the computer interprets the instructions. Right now I have nothing loaded, so it says it's a no-op instruction. The program counter is here, it's all set to 0, and the instruction opcode, all of these are set at 0 right now because I have nothing loaded. So first, what I can show you is that there's not too many different things in our simulator, but if we do open a file, let's say we open a file that I prepared here, SM213.s, which I actually have right over here. Oops, not this one. Right here, I just have kind of a small simulator file of just kind of random instructions that I've been working around that I'll talk about later. But here we have our main instruction starting point. Here we have a bunch of instructions, then we have a halt, and then we have a couple declarations of values we are storing into RAM. So these position flags tell us the address in memory that we want to start writing these either instructions or values. So here we are saying that address 100 in hexadecimal, we start writing these instructions. And here at position OX 100, we want to declare this position as call it I, and we are storing the value 5 in it. And same thing here, we have some other things that we've stored. I've made 3 integer variables, I, x, and y, and also an array that we can work with, stored at position 4000. And I've just loaded some dummy values into it. So let's see what happens if we if we try to load this program. So I'll click open, and it seems nothing happened. However, something actually did happen. If we look down here, it says we have an assembly error on my file on line 7 and character 21. It says no available alternate at input. So this is a problem you might face, and that just means that there is a syntax error somewhere in your code. So luckily enough, it actually tells us where in the code it is. So we'll look at line 7, line 21. And so line 7 is this one. And I have seen that I've actually made a small mistake here where I'm doing a load immediate instruction, and in order to do a load immediate, I can't just write the value. I need to put a $sign there to indicate that this is a literal number I'm trying to load. So I'll just save that again and see if we can load it this time. So we'll open the SM213, And wow, there we go. So there's a lot to look at right now. I'll just make that a bit smaller. So in order to kind of parse this interface, there's kind of two sections that we want to look at. If I open my file again, first we have this section containing our instructions, and that's right here in the middle. We see that at our position declaration at address 100 up here, we've written some bytes of data, and well, in this case, it's actually instructions, and this part is telling us how those instructions are interpreted. We see our load instructions and also our label main that I've called the start of our instructions entry point. And then on the right here is kind of our memory for our data. We see that at our position declarations 1000, 2000, and 4000, we have our values that we stored here in 5, 1C, and all these values here. And it gives us, and it tells us the address, the 4 bytes that are associated with its integer, because all of our data types that we're working with in SM213 are 4-byte integers. So this is going to be the byte at address 1000, address 1001, 1002, and 1003. And so here it says if we interpret this 4-byte if we interpret that's 4 bytes in memory as an integer, we get the value 5. And reference here is empty because it's not referencing anything. And we have the label that we labeled down here and any comments that I made over here. And you'll see that this machine is a little endian machine because we are storing the this is a big endian machine because we are storing the most significant bytes first and the least significant bytes last. So that is how that is working. So if we want to run this program, we have a couple buttons at the top. And so we have something called we have a run button here, we have a step button, and we have a run slowly button. And so what we want to do usually if you're trying to debug your program is you can click the step button and it'll step through each line of the program. Here first we have a load instruction, and it actually highlights that this load instruction is a 6-byte instruction here. And if we see in the program counter down here, it says the program counter is 100, which means that this is pointing to this instruction over here. We can actually change which instruction we want to start at by just kind of double clicking anywhere here in the instructions. And now if I double clicked here, this green bar will show up on this instruction instead, and it'll say the PC is at 118. And so the instruction that is highlighted is going to be the next instruction the computer executes once we click run or step. So I'll just start this back at 1000. And if we click step, we'll see that the blue is showing what instruction is being executed right now down here. And we can see that we just loaded, we have the current instruction and we have all the instruction values down here. And so what we have seen here is that this load instruction is loading the address of x into R0. And now we see that we've loaded the address of x, which we declared at 2000 over here, and we've loaded that into register 0. And so this is in hexadecimal, you have to remember. And if we interpret this as an integer in base 10, this is 8192. And if this is a reference, we are saying that this is actually referencing the x variable or x label over there. So one thing to keep in mind is that this reference is only telling us if we interpret this whatever value is in the register as a memory address, and as int is if we're interpreting as just an integer. That means if we want to store a value like 4096, which is in hexadecimal 1000, so say 4096, and I just wanted to store that as a number, even though perhaps I only want to use it as a number, the SM213 will say, hey, even though you want to store that as a number, by the way, if you interpreted that number as address, it references I, the integer I over here, because we declared it at address 1000. But anyways, that's just some aside of how this references works, because remember, in computers, everything is just bits, and it's up to us how we interpret it, either as a memory address, which is what the reference means, or as an actual number as integer. So what I'll do is I kind of mess with the data right now, and I will just kind of reset the data. And so that changes everything back. And you'll notice that resetting the data doesn't actually reset any of the registers. Now, why is that? Well, generally, when you're writing any computer assembly code, you can't allow your code to depend on any values in the registers before it's executing. Because the registers, they could be initialized to undefined values. So that's why when you're working with any of the registers, you always assume that they're undefined, and when you need to actually put a value in it, you want to load the specific value you want. But in this case, I will just put this at 0, so it's kind of like if we just open the program. And it'll go back to this first instruction. So we start from the top, and again, I'll click step. You'll see that we are loading this value into our 0. And if we click step again, we'll see that each of these instructions are one at a time executed, and we'll see our registers are getting changed and our values over here in memory are getting changed based on whatever instructions we want. So we can step through this all we want here right now. And in this second to last instruction, I have an actual break statement, which is just checking if my y is greater than 0. So right now it's always going to be greater than 0. So it's just going to loop forever for right now. And if I actually change this in memory to -1, you'll see that we can actually edit these things directly. Now if I keep stepping through this, you'll see that it now doesn't jump and goes onto the halt. So once it reaches the halt, I can keep clicking step and it just doesn't do anything. All right. So that is kind of all there is to how this simulator works. And there's other things that I want to show you, which is that if we don't want to step through each individual instructions, we can actually click this run button and it will just run all the way from the start to the end. So it'll run pretty fast actually because we don't have that many instructions, and we just jump right to the end and we'll see whatever all the values are being updated in the registers and also in memory. Another cool feature is that perhaps once you get larger programs, you don't want to click through every single instruction, but there's a certain point that you want to get to instructions to begin with and start executing from there. And what we can do is we can actually set breakpoints in this simulator, and that's what this kind of column right here. If we click and we want to set a breakpoint here, what this will do, and we start if we go back to the top again, what this will do is it's like a breakpoint in any other program, and if we click run, it'll run up to the breakpoint, and then you can start stepping through it and debugging it much more slowly. And we can set another breakpoint down here and just if we keep stepping through it, or actually if we run, it'll go to the next breakpoint. And so that's one way you can debug your program. Interestingly, this simulator also has some nice animations to show you that I can show you of how it's moving the data around within the registers and memory. So let me just reset the data, and the registers are going to be kept as is. If I click show animation and I say run slowly, let me just make the animations a bit slower, and we'll click run slowly. What it'll do is it'll kind of show you, once it loads instructions, what it's doing at each step and where it's getting the values from and where it's putting values to and where it's reading values to. So this is a very good way to visualize how the simulator is running based on your code. And generally, once you kind of understand how all the instructions work, you'll probably want to turn this off because it can get quite slow and not that useful anymore when you do understand what's going on. But when you're beginning, this is definitely a great way to visualize what each of the individual instructions are doing. So we can actually make this a bit faster. I think, yeah, there we go. And I'll just pause that. I'll do the hide animations, and we can see that it goes back to stepping through each individual instruction, and it just reached its breakpoint, so it stopped. I can say run slowly again, and I'll run to the very end. Well, in this case, it didn't end because it looped back. So that is all I want to let you guys know about how the simulator works. And given that the rest of the kind of difficult part is writing the actual code, I'm actually going to move on to the next section of this, which is kind of explaining to you what this kind of code does and just introducing you guys to some of the instructions that we use. So this code is just arbitrary code that I've written that uses some of the instructions, and it just does some random stuff with the array and the 3 integer values we have, but it does show some of the features of how some of the instructions work. So if I just kind of reinitialize all of these to 0, and I reset the data, so it's going to the beginning, and I go back to the very top of our main function. First, let's see what this load does. And if you guys are familiar with all the instructions, then you really don't need to watch the rest of this video, but otherwise we'll go through this load. So we see that we have a load and we have a $ into a register. What this instruction is, this is a load immediate instruction, and what it's telling the CPUs do is to get the value of the address of X and put it into R0. And you'll see a common theme amongst all the instructions in the SM213 is that when you have two registers that, or two arguments for the instructions, whatever the value of that instruction comes out to be is placed into the second argument. So when I read this load instruction, I'm placing the value of the address of X into R0. And if we if we step through this instruction, that's exactly what happens. The address of X is 1000 in hex, and that gets placed into R0 right here. Now this next instruction is called a offset load instruction. And another common thing you'll see within our instructions is that if we have something that we want to interpret as an address, we will have parentheses around it. In this case, we want to load a value from the address. We want to load the actual value of X and not just the address. So once we do have the address over here, these parentheses means that we want to interpret this as an address and read the value from that address. And this 0 here is just an offset saying that if we have a specific address, do we want to read an offset from it? And in this case, we don't actually need to read an offset. We'll just read it at offset 0. So after this instruction, we'll see that the value of X, which is currently at 1, will get put into register 0. If we step through that, we'll see that's exactly what happens over here. Next, we have something similar. We'll load an immediate value into R1, and this is the address of an array, 4000. And if we step through that, we'll see that 4000 is loaded into the register, and it tells us this is an integer. Well, if we interpret it as an integer, it looks like something like that. And if we interpret as a memory address, it's going to reference this array. Next, what we have is we want to store. We have a store instruction where we're storing the value of R0 into the address of R1. And again, this is kind of the same thing where generally when we have something that needs to get put somewhere, we put it into the second argument. And since this is a store instruction, we are storing something into memory, and that's why we want to interpret whatever the value of R1 is as an address. In this case, R1 is the array, and R0 is equal to X that we loaded before. Generally, writing the comments for yourself can help keep track of what things are. And now what we can do is if we have loaded X into R0, this instruction should set array of index 0 to 1. And let's see if that happens. And that's exactly what happens. Next, what we have is we have an indexed, sorry, that's not right there yet. Next, we have another load immediate instruction. And this time we are telling the computer to load just the value 0x2 into R2. I actually have a incorrect comment here. I'm saying R1 is equal to 2, but this should say R2 is equal to, and I can actually edit that comment directly like that and save that instruction. And now if I open if I reopen this here, I should, oh no, I need to reopen it again. Yeah, there we go. Now it says R2 is equal to 2. So yeah, you can definitely edit the instructions. You can also edit the instructions itself if you want to change it into a store or something like that, but that's not going to be valid syntax, but you can change the instructions here as well. So this next instruction should load 2 into R2, and we'll see that that's exactly what it does. R2 is now equal to 2. And this instruction is a index load. So the 3 arguments that are in this parentheses is the first argument is the base address of the array. And in this case, it's R1. We're saying the base address is 4000. The second argument is what the index is. In this case, we have R2 storing the index, and we have 2 as the value of the index. And what this load instruction will do is it'll offset from the base address whatever the index is times 4. Because all of our ints are 4 bytes, if we want to get the first integer or the 0th integer, we have an offset of 0. If we want to get the if we want to get the first index, then we have to do offset of 4, and so on and so forth, 8, C, and then 16. And so this is a way we can do indexed loads into a register. And again, the second argument of our instruction is where we're placing that value. So we're going to be reading from array of index 2 and placing that into R2. So array of index 2 is actually 13 right now. And if we place that into R2, that means we should get 13 into R2, and that is exactly what we get. Now, we've mentioned before, or potentially not yet, but our instruction architecture actually doesn't implement any subtraction. So if you want to use a subtraction, that's the same thing as adding a negative number. So when we want to get a negative number with 2's complement, we can do this very common instruction that you'll see throughout the course, which is we'll do a not and then increment. So what this is doing a bitwise not operation on the value of R2, or the address, sorry, the register R2, and then we increment it by 1, and that will actually get the negative value of whatever is in R2. And in this case, it's going to be negative 13. And well, let's see if that's what we get. So we'll step through the not, and that gives some the bitwise not of 13, and then we'll increment by 1, and that gives us negative 13, right? So now R2 is storing negative array at index 2. Now what this next instruction does is we are doing another store instruction, except now we are utilizing that offset. We are taking whatever is in R2 and we want to place it into R1, interpreted as an address, offset by 8 bytes. And what is R1 again? That is our array. And array, if we offset by 8 bytes, which means we add 8 to the address, that's going to be 4008. And 4008 as an address references array at index 2. So what this instruction is doing is we're saying we want to set array index 2 equals R0, which is negative array index 2 before. So what these last 4 instructions do is just inverts the value of an array 2. And if we step through this again, we'll see that now array 2 is negative 13, while when it was before positive 13. Our next instruction here, we just are loading another value. This is also very common to instruction you'll see, is to load the address of a variable and then load the value with offset 0. So we'll step through that. We set R0 to the address of I, which is again that, and we'll load the value at that address, and we'll store that into R0 again. So now we'll see that this R0 should change from 4096 to 5, and that is what we see here. Now what we want to do in this next instruction is we're saying we want to load from the R1 as a base address offset by hexadecimal 10, which is 16 as a base 10 number. And so R1 is storing, again, the base address of the array. And if we offset by 16, what that is going to get us is this address here, 4010 in hexadecimal. And that is the value of array at index 4. So what we'll see here now is our R2 should get 11. And if we step through this instruction again, we'll see that now R2 is equal to 11. Another thing you'll notice is that our implementation of SM213 doesn't have any multiplication or division instructions. Now, you could do multiplication or division by successive addition or successive addition of negative numbers for division and seeing how many times it goes into it. But since things are in binary and generally we'll be working with powers of 2, if you remember from the first couple of lectures, we can do a shift, a bitwise shift left or right to represent a multiplication by powers of 2 if we do a shift left, or divisions of power of 2 if we shift right. So this next instruction is a left shift, and we give it how many bits we want to shift as a literal number. And in this case, we say we're shifting by 2 bits, and we want to shift whatever is in R2 by 2 bits left. So now we'll see that if we shift R2 by 2 bits left, what that is equivalently doing is multiplying it by 4. And if we step through this shift, we should see now we have multiplied it by 4, and if we interpret it as an int, it becomes 44. Now we do is, when we have our next instruction is an add instruction. Again, whenever we have a value calculated by an address, generally we are storing it into whatever the second argument is here. So we're going to add R0 and R2, and we are storing it into R2. And R0 before, what we did was, oh yeah, we loaded I into R0, and R2 is equal to some arbitrary thing that I did. I just did array index 4 times 4. And once we do that, R2 should have the value of array at index 4 times 4 plus I. So we should get 49. And if we step through, that's exactly what we get. Now, what we can do, we have another store instruction, and this is actually an index store instruction. We have the value that we want to store in R2, which is 49, and we want to store it into this array index. And so the base address of the array, again, is R1, so that's starting at address 4000, and we want to index by R0. R0 currently here is equal to I, which is equal to 5. So what this instruction should do is store whatever is in R2 into array index 5. And let's see if that's what it does. So we'll store 49 into array index 5, and we'll see 49 is stored. Finally, I also want to introduce kind of why the program counter is, how the program counter interacts with some of our jump instructions. So we'll see that currently our program counter is saying that we are our next instruction is 12E, that's our program counter. And when we step through this instruction and loading the address of Y into R0, we'll load Y into R0, and we'll see that the program counter has incremented, and now looking at the next instruction. So we'll load the value of Y into R0 again by stepping through here. And then the next instruction we're pointing to is a break or break if greater than. So what this instruction does is it checks the value in whatever register we give it, in this case R1, and if it is greater than 0, we want to jump to whatever we called main. And if we remember from our input file, we called our main instruction, from our input file, we said the beginning of all these instructions was called main, and that's why there's a label here saying this is main. So if we load Y into R0, and in this case Y is 12, we'll see that because Y is greater than 12 is greater than 0, this branch will branch to main, which is back up here. And you'll see that when we click step, we'll see that we just executed its instruction, which is why it's in blue, but now our program counter is pointing back to wherever main is, where we just took that jump, and now we're back here. And so this is going to be an infinite loop right now because I never actually changed the value of Y. It's always going to be positive. So this is just going to loop forever and keep doing stuff like this. So if we keep going back here, we'll see that we'll redo everything, all the values are back the same, and keep looping through through main. So in this case, again, I mentioned before that these instructions are just arbitrary, and just wanted to show you how they'll work with the proper comments so that you can use these instructions in your own code that is actually executing something useful. And I will say again that because we have an infinite loop, if I click run, we'll see that this is just going to loop forever, and it's going to be updating a bunch of values and not doing very much and going in circles. And this is not something you want to do in your code. And if that does happen, we have a halt instruction, and we just tell it it's going to stop somewhere. In this case, if I manually make this a negative number, and we just set it to -1, we'll see that if we step through this, we read Y, and we get the value of Y, it's -1, and we check if -1 is greater than 0. In this case, it's not, so that means that it should go to the next instruction and not jump back to the top of the main. And if we step through that, we'll see it goes to the halt instruction next, and now if we keep stepping through, it just ends the execution. So, and that is kind of the same as before. If we run from the top now, it'll just run through once and stop at the very bottom. So overall, I hope this was helpful for you, and you took something out of this video of how our simulator works and how its interface works, and I'll wish you the best of luck for the rest of the course. And if there's anything I missed, maybe I'll make a follow-up video, but other than that, good luck.